Lab 4, we are observing the motion of a mass attached to a spring that swings in an arc while also oscillating on that spring. I chose the system to be the spring, the mass, and the Earth. So, using Tracker, we were able to analyze this motion and find the x and y position data. We then created a computational model and finally found that the predicted motion followed a similar pattern as the observed data received from Tracker, and therefore that the spring mass system satisfies the energy principle. Some of the main principles used in this lab were Newton's second law, the energy principle, and Hooke's law. The momentum principle was used to find the spring's new velocity and position. The energy principle, which is the sum of the kinetic, gravitational potential, and spring potential energy, was used to find the total energy of the system. And finally, Hooke's law aided in determining the spring's stiffness and relaxed length of the spring. In Tracker, I set the length scale as 0.70 meters. I then chose the coordinate system so that the origin is at the attachment point and that the negative direction of the y-axis is pointing downwards. Also, I set the mass as 0.402 kilograms. Then, when finding the point mass at every location, I got these x and y positions. I then saved these positions to a CSV file, which I will use to compare with the motion predictions. In GlowScript, I set the mass of the ball, its initial observed position, velocity, and time. Next, in order to calculate the weight and spring force acting on the mass, we can use our data to get the period of oscillation and therefore the spring stiffness for the spring, which I got to be 6.78 newtons per meter. And then, using the static equilibrium, I found the relaxed length of the spring to be 0.125 meters. I also have the gravitational force to be 9.8 meters per second squared, and the time step given as 1/210 seconds. This is the code that calculates the length of the spring at each time interval, where L hat is the spring's direction, and S is the stretch or compression of the string, and is used when calculating the spring's force and spring energy. The energies that are present in the system are the kinetic energy, gravitational potential, and spring potential energy, and we must calculate their initial energy changes, which is calculated using these equations. Now entering the while loop, we set t to be less than 9.307 seconds, the final time observed, and define the initial energies, which we calculated before, and will use later on when finding the overall energy change. Next, we calculate the net force as the gravitational force plus the spring force, and then use Newton's second law to predict the new velocity and position at each time interval. Then the spring is updated as the position of the system changes. So does the stretch and compression of the spring, and this code updates the visual model. The last thing that updates is the new energy of the system as the time interval changes. The kinetic, gravitational potential, and spring potential energies change and have to be recalculated. When we run the code, we get a graph that compares the computational data with the observed. We can see that while the graphs are pretty similar, there's still a slight discrepancy in the motion. This is because of the added drag force to the system and some other rounding errors in my data. In response to the what does it mean question, is the energy principle satisfied? As you can see in this graph of the energies in the system, where the blue line is the change in the kinetic energy, red is the change in the spring potential energy, green is the change in the gravitational potential energy, and yellow is the total change of energy, which we can see here is 0. Because the total energy is 0, we can see that the energy is conserved and therefore the principle is satisfied. Also, the energy principle equals the work done in the surroundings, but because the system is the mass, the spring, and the Earth, there are no surroundings, so we know that the work is 0, therefore providing that the change in energy is in fact 0. Now, in comparing the period of oscillation from the x position data to the y position data, we can see that the values differ as each equation compares different values. In the x direction, the equation is based on the length and gravity, whereas the y direction is based on the mass and stiffness. Also, as we can see in the computational model's motion, it takes more time to move one cycle in the x direction than it does to move in the y direction.